All right. So one thing I wanted to mention before we dive into this, you asked me last class, the answer was set to only one. Technically, there was two correct answers to that in-class quiz. I kind of didn't look at it close because I knew I was just going to use it to give points for kind of being here. But technically, if we're thinking about these nonlinear models and we include squared terms, what are we really doing? We're adding a separate variable, right? So if I add variables into my regression, what should always happen to my R squared? Always increase. Now, what I meant the question to say was what happens to my adjusted R squared? I don't necessarily know, right? Having that additional variable is going to help, but if it doesn't allow me to explain more of the variation in that Y variable, potentially goes down. So the answer there is always going to be if you add more variables in, we'll kind of use some of that today, you'll always see the R squared go up, but not necessarily adjusted R squared, okay? So we'll get started here today. I don't really have anything new to kind of mention logistics wise. So you've got that quiz 4 that I posted after last class. Let's do at the end of the day Monday. So that's related to everything that we talked about prior to spring break and last class. I call it nonlinear relationships. We're going to kind of call it, we do nonlinear relationships today as well. But that quiz is only from what we covered last class and prior to spring break. Okay. Same kind of thing with that problem set. For a couple of you that showed up yesterday that didn't get questions in because my B251 students were very nervous about their exam today. I'm going to have some additional office hours on Friday, which I have it in my Outlook schedule, but let's see. So I said I'll add some this Friday from 9:30 to 12:30. Nope. Where is this at? I jumped this up a week. So this should not be April 3rd. Sorry, this should be the 27th, right? Tomorrow. So I'll be in my office from 9:30 to 12:30. If you want to stop by, any additional questions on that problem set or questions before you take that quiz. I'll still have, because I don't have office hours next Monday. I only have office hours on Wednesday. So I am going to add office hours next Friday in that same time slot. So this Friday and next Friday, 9:30 to 12:30, I'll have office hours. I only have my Wednesday office hours next week, which that's when the problem set is due at the end of the day. So if you have last minute questions, you could go to those office hours on Wednesday. I won't be around on Monday, unfortunately. I've got some other commitments that are going to keep me away from campus. Is that everyone clear on that? Any questions? Okay. So what we're going to do today, go to that homepage. So kind of week 10, nonlinear regression continued, which we really could call interaction terms as this next topic that we're going to cover, right? It's still looking at nonlinear relationships, but it's going to be a little bit different than what we were talking about, looking at like natural log models or squared models. So let's get started, okay? So let's say I was running this regression and I have wage as my Y variable, and I've got two dummy variables, right? Whether or not the individual's female and whether or not they're married, okay? So this is kind of our typical, we've looked at this before, linear regression. And, what do these coefficients really tell me when I'm just running these dummy variables without any included, controls? What this is really doing is telling me when the individual is female, here's the expected change in their wage. So what it's really telling me is the average change in the wage for a female relative to the zero group, which is a male. And then what would beta 2 tell me? It's the predicted increase in wage on average for someone who is married versus someone who's not. So we can almost think about what we're doing here is I'm trying to kind of predict wage, right? And without any additional controls, I don't really have an X variable. So I was interested, maybe of the relationship between age and wages. So I had something like this. But I included these dummy variables for, I think this lines up with the slides, whether they were female and whether or not they were married. So we said with dummy variables, the way we can think about this is, let's say age was 0, and a weird thought experiment. But what would beta 0 represent? The predicted wage if all these variables were equal to 0. So when I'm looking at beta 0, this is the predicted wage for who? Someone who is male, right? And someone who is not married. Okay. So this would kind of be like our unmarried male kind of starting point for that wage. if I think about for someone who is female but unmarried, what would change here? Well, I'd have a 1, I'd have a 0. So where would my wage start at? Let's assume, probably more realistically, given the discrimination and oops, not beta 1, that if beta 2 is negative, well, what we're actually saying here is for an unmarried female, the predicted starting wage starts lower. Now that relationship between age and wage might still look is going to, from this regression look the same. So if I'm trying to predict wage using age, the slope of that line of best fit is still that coefficient on that X variable I'm looking at age. Now, for the unmarried females, their starting point changes, but the relationship between wage and age for them, we haven't allowed to change at all. We'll talk about we can, but for now we haven't. So we include these dummy variables, essentially changing our starting point. Okay? And then I could think about, okay, what if I had a married female, right? Well, then my starting point would be what? Maybe it's up here. Beta 0 plus beta 2 plus beta 3. And that would represent kind of my starting point for a married male. And then I could do another one, right? Maybe I have a married female, and then I can kind of plot that point. But when we're using dummy variables, whatever that continuous variable we were interested in age, that relationship between age and wage stays the same. The dummy variables just kind of change the starting point. Okay? Now, drew something similar to this when we were just including one dummy variable. So what I might want to do instead of having, let's say I have like a bunch of dummy variables here, or even I only have 2 here, I might want to know the different starting points of wage for a married male, a married female, an unmarried male, or an unmarried female. I would kind of have those 4 different categories. Okay? So what's another way that we can actually get at? Because I can look here and say, okay, the difference between an unmarried male and a married male is this. Difference between a married male, unmarried female would be the difference in this starting point. There's an easier way to do this in our regressions. Okay, so what we're going to do, I'm jumping the gun a little bit here, but I'll show you some regression results in a second. So let's instead try to predict wages. And maybe I have this additional control, all right, looking at age, but then I also say, okay, take my male and my married variables, but I'm now also going to include what we call an interaction between the two, right? So now I'm going to take an interaction where I multiply the male dummy variable by the married dummy variable. So first of all, if I include an interaction term, what's definitely going to happen to my R squared? I've essentially included in additional variables, so my R squared has to go up. Now, what about my adjusted R squared? Don't really know. Right? Now, most likely in this case, because we're not trying to fit like a different functional form, it's likely that this is just providing me more information. It's probably going to increase that adjusted R squared as well. But we do get penalized for adding in that additional variable. So we really can't say. We can only say for certain the R squared will go up. The adjusted R squared is penalized for adding this additional variable. We don't necessarily know. Okay? But you can imagine like there might be an interaction between these variables, right? Because there could be some discrimination going on against unmarried females that is different from the discrimination against married females, right? So there could be this kind of interaction between these two variables that matters. So what you could think about here is if I'm now wanting to predict kind of that starting point for wages, where would that be? So I've got 4 different groups, right? What if I had, do the easy one first, an unmarried, oh, what did I have here? I changed this on accident. Sorry, this was supposed to be female, right, from our original one. So this was, just kind of keep this easier. Female times married. So let's say I had an unmarried male here. What would the value of male or female be? 0. What would the value of married be? 0, what would the value of the interaction be? Well, this is 0 and this is 0. 0 times 0 is 0. So our unmarried males would still kind of start out at that same intercept, just the constant. But what about if I had a married male? Well, now, if I'm kind of trying to make that prediction when age is equal to 0, now female is equal to 0, married is equal to 1. If I take 0 times 1, that would be, so this doesn't get added in. So if we're thinking about a married male, we might have beta 0 plus beta 2. Okay. Maybe, in the workplace, if you're married, that shows the company you're a little more stable. And so maybe they reward you, right? They give you higher wages. I don't know what the actual values are, but this is kind of some intuition that maybe we're using. So I then got other groups. So let's think about now, if I had a married female. Yeah.
Wouldn't that be beta 3 instead of beta 2 for a married?
Oh, sorry. Yep, because I changed. You're right. All right, I had a male, so that was 0, and then 3 was the married variable. I switched those, sorry. So if I have a married female, right, what is this variable going to be? 1. What is the married variable going to be? A 1, but what is that interaction now going to be? 1 times 1 is 1. So it's almost like I included a third dummy variable, right? So now I could think about, okay, for those married females, I'll have beta 0 plus beta 2 plus beta 3 plus beta 4. Now, it doesn't always have to be that's higher. I'm assuming here the coefficients are positive, but you could, they could be anywhere depending on the sign of those coefficients. I then kind of have one more group, which is an unmarried female. So here, if I had an unmarried female, beta 3 is, they're unmarried, 0. Sorry, not beta 3, but married is going to be 0. Female is going to be 1. What's 1 times 0? 0. So the only thing that we would have, I don't know, here I'll assume it's negative, might be beta 0 plus beta 2. So those starting points, it's kind of still similar to what we were doing over here, but it now gives me this additional coefficient beta 4, which is kind of nice to interpret. Because how would I interpret beta 4? It's the predicted increase in wages for a married female relative to who? So if I have beta 2, that's simply the effect of being female. Right? Beta 3 is simply the effect of being married. Beta 4 is the effect of being married and being a female. So it's kind of like this change from beta 2 to beta 4 is the predicted change in wages for a female who is married. So it kind of tells us what this interaction is between these two variables, that potentially married females might be rewarded with different wages than a married male, because a married male, all that would be getting added into our predictions is beta 3. So we can kind of, and I'm doing this with two groups. You can imagine I could do this with 3 or 4 dummy variables there. I'm going to have a ton of interaction terms. It gets a little bit more difficult. I kind of keep things here with just interaction between 2 dummy variables. We can start to think of how about this is changing the starting point of that predicted Y value. But what this doesn't do is it doesn't allow for the relationship between the other non-dummy variable and your Y variable to change. So all of these would still be the same slope. Any questions on this before
I don't like. I guess I'm still a little bit confused on what the purpose of beta 4 is, like what it shows that they are.
Yeah, so essentially, if I'm married and I'm a male, what's the predicted change in my wage? Just beta 3, right? So it could be the case that if I'm a male and I'm married, maybe I get higher wages. What could be true is that being married females are treated differently, right? So what beta 4 is telling me is if I go from unmarried to married, but I'm a female, potentially my wages actually go down, right? So here it's picking up the fact that being married could have a very different effect for males than it could be for females.
Okay.
And if I'm not including that interaction term, I'm not able to pick that up. This is the average effect of being female. This is the average effect of being married, but potentially they're like incorporating the fact that, well, maybe males and females are treated differently when they're married, right? Including that interaction term allows us to identify what that difference might be. Right? What's another good example? I would think about maybe, so maybe if you're just looking at, is someone awarded a scholarship, right? And then what's the effect of being an upper versus a lower classman, right? And then maybe that's treated differently if that individual is also, I don't know, you could do international student versus not, right? Maybe, for whatever reason, I don't know what the intuition is, but right, we're able to identify our international students being treated differently in terms of being awarded a scholarship if they're upper or underclassmen relative to a non-international student, right? So really what this is allowing us to do a lot of the times is you can identify some discrimination that's going on between different groups, that maybe there's something that's being rewarded in terms of wages that varies between another group. So maybe being married has a positive effect on wages for males, but firms are treating married females in the exact opposite direction. I don't know if that's the case, but my inclination would be potentially that could occur. Okay. Any other questions on this? Kind of look at some regression results here in a second. Okay. So here I ran this without the interaction term. And I can see, okay, on average, if I don't allow for this difference to exist between the effect of being married between males and females, simply being a female actually decreases wages. So this would be some identification that we've got some discrimination going on. Okay? Now, what is true about being married? It looks like it actually increases the predicted wages. But I said maybe being married, that's the average effect across both males and females of being married. Well, if I'm getting the average effect, so think about it this way. What if the effect for males of being married was positive and the effect of females being married was negative? If I don't include that interaction, what could I see the effect of being married be? One's positive, one's negative. I could actually see no effect. But that's not the case. There is an effect. It just varies across a different group. So, here, both are statistically significant, right? So it's not that I didn't find zero effect, but this is just the average effect of being married. So what I'm now going to do is include that interaction term, right? And think about what is the total effect of being married for a female? It would be beta 2 plus beta 3. Right? Because now if I'm a married female, what is this? 1 times 1. Now that gets added into my prediction. So really, even when we include these interaction terms, you can still think about, we can predict y. It's just we have to, a dummy times a dummy. The only time that's 1 is if both of those variables are equal to 1. So if I include that interaction term, notice what do we end up with? Well, the effect of being female still looks like it's negative, right? It's an even larger amount. Right? The effect of being married and having a positive effect. But what is that effect now of being married? It's only for what group? So if it was the effect of females, what would the effect of being married be for a female? It would be this amount plus the coefficient on the interaction term. So this would represent the effect of being married for whatever the other dummy variable that you include an interaction term for was equal to 0. So in our case, that group that was 0, the other variable is female, that would be our males. So this is the effect of being married for a male. Looks like they're rewarded with higher wages. Now, what would the total effect of being married be for a female? Well, this is going to be the effect of being married. Here's the additional effect of being married if I'm a female. So I would actually add these up. It ends up being what? Negative about 0.05. So the total effect of being married in terms of on wages is actually positive for males, but the total effect of being married for females is actually negative. And how much lower would the predicted wage be for a married female relative to a married male? That's the difference between those two. Okay. So, this is allowing for that effect of being married not to be the average effect across both groups, but we can identify the effect for each group by including this interaction term. And notice here, highly statistically significant. This is evidence that firms are rewarding married males very differently than married females, right? Now, this is a slightly older data set, so this might not be like, hopefully things have changed, right? But this is, some older data, some evidence that we have discrimination, or that we have some evidence that firms are treating males and females differently in respect to these other variables, in this case, marriage.
So just to reiterate, for some married in this, our output, the first one, right, coefficient, the first three, that is just pertaining to married males, correct?
Yep.
And then
And the reason why is because, remember, when we're interpreting these coefficients, what do I always have to throw onto the end? Holding all else constant. So this is the effect of being married, holding whether or not they were female constant, right? So it's almost like we're only looking at married males, what's the effect? But then if the female holding this constant, well, they're female, so this is equal to 1. So we're essentially saying this would be kind of our total effect for a married female. The effect of being married, but also the effect of being married when I'm a female, right? We've included that interaction. So let's think about here. What would the effect of an unmarried female be on wages? Well, if they're unmarried and they're a female, what is this variable equal to? 0, because they're unmarried. So the only effect on my wages of an unmarried female would simply be the coefficient on female. So what's the difference between being female and unmarried and being female and married? The difference between these two coefficients, right? This was just the effect of being female. If this wasn't equal to 1, right, I was unmarried. This is the effect of being female if I am married, when it is equal to 1. So then I've noticed here that difference in our predicted wages looks like if I'm a married female, my wages don't go down quite as much, right? That difference, if I'm thinking about, instead of being negative 0.25, or sorry, I said this the opposite way. I think I said opposite. So the effect of a married female, it actually lowers my wages even more, right? Because I'm adding in, I've got 2 negative signs here now. So the effect on my wages of being a married female would be negative 0.25 plus a negative 0.21, giving me like negative what, 0.46, right? So there's an even larger decrease in the predicted wages for a married female relative to an unmarried female. And I think if you go through like the economic kind of model, it's something about like a married female is more likely to have a kid, more likely to take time off work. And so firms might be treating these individuals differently. And we see that play out in the data. So this gets harder to think about. So we'll talk about this today. I'll probably revisit it next week as well. So we'll just get more examples, but this is kind of our initial start. Any other questions on this before we keep going? So predicted wages, we said here for males that are married, because if they're male, these two would be equal to 1. The only thing added in is kind of 0.16. And then we add the effect of being married and females. Well, the effect of being married from a female is actually lower. In fact, it flips signs, right? It went from 0.16 to, we said negative 0.05 when we add those two coefficients together. Okay. I think there we go. Okay. So I kind of already jumped kind of out of order a little bit, but essentially these interaction terms tell us like the difference in the starting points for that Y variable across these different groups. So if I have 2 dummy variables, I essentially have 4 groups, right? 0, 0, 0, 1, 1, 0, 1, 1. Right? So it allows me kind of to pick up these differences in the starting point for that Y variable. Okay? So let's look at this in Stata. It's not terrible, right? In fact, really all we're doing, so if I go to kind of this interaction terms, I believe I have it sitting right here, that do file. And I think here I just opened up this wage data that we just looked at. So what I can do is here was my kind of original regression. That was the results we looked at without the interaction term. Here's what it looks like with the interaction. So what we can do, oh, hold on. This is not what I wanted. We started out here. I'm going to come back to this later. So we were looking at female and married, right? That was the example we had. To include the interaction term, you could generate a new variable, right? So if I wanted the interaction term between female and married, what would I do? I generate a new variable where I took female and multiplied it by married. I have another syntax we can use in Stata, kind of similar. I showed you this when we wanted to create that square term. Basically, a double hashtag here, a double number sign, says take this variable and multiply it by this variable, but include the variables themselves and the term where I've multiplied one by the other. Okay. So just like when I did this with the same variable, it included the linear term and the square term. This will include female, married, and the interaction. Now, if it's easier for you to think about, you can create that interaction term yourself. By doing something like this, all right? Now, why might I prefer to do it this way? I mean, it's not as efficient in terms of coding, but for me, it's a little bit easier to think about when I then see the results. So I'll kind of show you the difference here. Hopefully, when I run these two regressions, if I'm not lying to you, I get the exact same results. It's just two different ways of doing the same thing. Now, why I might create the variable myself is because if I then said, let's say I asked you for the total effect of being married for a female. All right. So we said, if I can get this, there we go. And I'll upload these kind of edits after class as well. All right. So what would the total effect on my wages be for a married female? Well, it would be, or actually, no, let's do it this way. This might make a little more sense. What's the marginal effect of being married for a female? Well, if I'm married, this would be a 1. So my predicted wages would go up by whatever that coefficient was on female. But it would also go up by, well, if they're a married female, it would also be the coefficient on that interaction term. So here, when I'm using kind of this underscore B, I want to take that coefficient on the interaction term, it might be easier to think about it this way. Now, I can still do it if I've used the double kind of number sign or hashtag sign here. But what I would need to do is I think it's what? It would look like this, right? So it's just a little different in my coding, but I might forget I need a number sign. I might put 2 number signs and it doesn't run it. So I think sometimes creating the additional variable yourself, it's a lot easier to think about than pulling that coefficient from the regression results. Does that make sense what I'm saying there? Any questions on that? But really, this is just 2 different ways of getting to the same result. It's just slight differences in the coding. So if I'm using chat probably tells me to do this. Chat GPT, all right? Probably doesn't tell me to create the variable myself. I don't really know what exactly to do, but there's 2 different ways to do this. Any other questions on this? So I'm going to skip this for now. We might come back to this next week if we have time. It's just a different way of thinking about these interaction terms. I'm actually going to come down here and show you a different example. So let me make sure I get my global path set correct. I'm going to open up this traffic stop data. There we go. And I'm going to generate some of these variables. So this was just a dummy variable that at the traffic stop, it's a 1 if the result of the stop equal 2. That meant a ticket was issued. And then all the other things were that a ticket wasn't issued. I forget what all the other options are. This is a dummy variable. 1 if they got a ticket when there was a traffic stop, 0 if not. Oh, sorry. Sometimes as we kind of progress, I've done this before. These are like these built-in data sets. So when I run this BQs, it's just these data sets that are stored in, I don't actually know the technical thing. They're not in the cloud. They're like in Stata somehow that they're not in Stata. They can access them from a website that Stata can access and kind of pull in these data sets that exist out there that only Stata has kind of this nice easy access to using that BQs command. Yep. And we'll kind of come back to this because there's an interesting other result we can look at this data set for. Okay. So when I'm using that traffic stop data, I'm going to create also these dummy variables that identify kind of the driver's race and then the officer's race. So here, I'm going to create these dummy variables. And my thought experiment was like, this is an interesting data set because what if I'm pulled over? Am I treated differently if I'm, and I think here I've just looked at, am I white or non-white? Am I treated differently if the officer is white or not white? Right? So maybe it's not just that people of different races are being discriminated against. Maybe they're being discriminated against even more if the officer is of the same or of a different race. Right? So we can kind of identify some potential discrimination and variation in that effect. Okay? So I've got all these dummy variables. Did I hit run already? Yeah, so I've got them all created. I'm then going to include this interaction, which is, was the driver white and was the officer white? Right? So my imagination is maybe, you know, if someone is of the same race as the officer, maybe they actually issue tickets at lower rates. I don't know, but we can see if that's the case. Right? So I create this interaction term. I then include the dummy for whether or not the driver was white, whether or not the officer was identified as white in this data set, and the interaction between the two. And I've got a bunch of other controls. So when we do these interaction terms, we can still include as many additional controls as we want. And that makes the regression results more powerful because now these interactions are telling us, is there a difference in the way that a white officer is treating white versus non-white drivers, holding all of these other things constant. So here I've got whether or not the officer was male, the driver was male, the driver's age, the officer's years of service, you know, maybe we'll been in the job longer, you know, issue tickets at higher rates or lower rates. And then here was actually a control. So when I use this IDOT command, I think I've shown you this maybe once before. So what it does is it automatically creates a bunch of dummy variables. And so the reason for the stop here, I forget, there was a bunch of different how it was coded, but it was something like speeding, you know, warrant out for the driver's unit. So there's like very different reasons why I could be pulled over. We're holding that constant. Okay. So if I now kind of come down here, run this regression where I include that interaction term, we get some interesting results. Okay. So holding everything else constant, if the driver is white, are they issued tickets at higher or lower rates? Well, it's a little bit different because here, this is the effect on the probability I was issued a ticket. Remember, when my y variable is a dummy variable, changes in my y variable are a change in the probability. And so we're still reusing these concepts we've talked about. So if the driver was white, but we only want to look at this coefficient, so the interaction has to be 0. So if the driver is white, what's the only way the interaction between the driver being white and the officer being white is equal to 0? If the officer was not white. So this is the effect of being, if the driver is white, the officer is not white, they issue tickets at lower rates. The probability goes down by about what? 0.01 or 1%. And it's statistically significant at the 90% level. We couldn't say that there's any effect at the 90, 95, or 99. Right? It doesn't quite meet our threshold. Where the more interesting results come from, I would argue, is if the driver is white and the officer is white. So what would the total effect of that situation be? Well, if the driver is white, the predicted probably goes down by 0.01. But then if the officer is also white, the probability they issue a ticket actually goes up by 0.02. So the total effect here is that for a white driver, if it's a white officer, the probability they issue a ticket actually goes up by 0.01, approximately. I'm rounding pretty egregiously here to the second decimal. So this is I wouldn't have expected this, which is that drivers are being treated, basically white officers are treating white drivers a little bit more intensely, right? They're issuing tickets at higher rates. So sometimes we'll get results that kind of go against our initial inclinations, but that's the whole reason why we want to use these data sets, because we don't want to just rely on what we think is happening. We want to use the actual data to say what is happening in the real world. Okay. And then, but what's even more interesting maybe from these results is doesn't say there's no discrimination point, right? Because let's think about what does the coefficient simply on my officer being white represent? Well, if the officer was white and the driver was white, what actually would I add up? I would add up every one of these coefficients, right? So kind of that marginal difference between am I issuing a ticket if I'm white versus the officer being white or non-white. Maybe that was that white drivers are issued tickets at slightly higher rates. But here, if I just look at this coefficient, what is that telling me? It's the probability that I issued a ticket if the officer is white, but the driver would have to be what? Yeah, because the other coefficients, if we're just simply focusing on that officer point, that tells me the probability a ticket is issued when the officer is white and the driver is non-white. What is that probability? It goes up by 0.06, right? So we've got here that yes, white officers are issuing white drivers tickets at slightly higher rates, but they're issuing, tickets to non-white drivers by an even larger amount, right? So we do have some evidence here that there's some discrimination going on. So this is, I think, hopefully kind of showing like the power of these interaction terms. We can now identify how one variable's effect might vary between two different groups.
But what about like non-white officer and the white driver?
Non-white officer and a white. So that would simply be here. Yep. Because if the driver is white, but the officer is not, these two would be equal to 0. We're just left with this. So this would actually tell us that white drivers are issued tickets from non-white officers non-white officers at slightly lower rates. Once again, might go against some of our intuition, but this is what the data says. Once again, this is an older data set. I don't know. I think this, if I remember right, this came from, I think what it says is a large city in Texas. I believe it's Houston. But this is kind of the results that we find. Any questions on this idea? So here we're just looking at interactions between dummy variables. We're going to go a little bit more into the weeds. I think that's the only example that I wanted to kind of throw in here. Yeah, so the next thing that we're going to look at is I can do these interaction terms. When I was saying that we were doing this with dummy yeah, sorry.
So you said that it's, non-white officer, white driver, right? In the first one. So if that other variable can exist, right? We had what? It's like white driver, white officer, right? If that didn't exist, what would our first one be? Could that also account for a non-white officer and
so if we didn't include the interaction term, so if we don't include the interaction term, I didn't run that regression, did I? So I can kind of show you what that looks like. So we'll copy this. Oops. So this is where the latter part of this class, I will answer as many questions as you guys have, and we'll kind of go off on limbs sometimes. We'll have plenty of time to kind of cover these. And so I think the more questions, I'll often kind of take that same data set and even add in things during class. So this is where being in class matters. So let's say I don't include that interaction term. I run this regression, and it looks like simply being white actually doesn't change the probability I'm issuing a ticket. We know that's not the case. We know it's just that this is the average effect of being a white driver across both white and non-white officers. Once I add in this additional interaction, I now can pick up the fact that being a white driver, I might be treated very differently by a non-white officer as I would be by a white officer. And then vice versa. You can do the opposite. Yep. And then here, once again, if the officer is white, maybe, this is just picking up the average effect of the officer being white. It could be that the officer being white, they're issuing tickets at different rates to white and non-white drivers. We haven't captured that at all here. We've only captured the average effect across those two groups if we don't include the interaction. Any other questions here before we keep moving? So the next thing we'll look at, and I'm sure this will spill over based off of where we're at in terms of time, into next class. So I did want to actually mention something here. Just before we kind of keep going, because we'll keep using this wage data set. I was kind of being lazy in my interpretation because I was just kind of showing you the predicted wage. This was actually using the natural log of wages. So let's get some practice doing some interpretation. All right. A lot of times when I was looking at these nonlinear models last class, we were looking at the effect of continuous variables. Here, if I've got a dummy variable, so let's say I want to know just the effect for an unmarried female. So I'm just looking at this coefficient. How would I actually interpret that coefficient? So what's a 1 unit change in the dummy variable? Going from being male to being female. So being female would change my predicted wages by, it would lower them by 0.25, but 0.25 what? So if I've taken the natural log of my y variable, it's going down by 0.25. But if I'm going from not a natural log to a natural log, it's like I'm going from a probability to a percentage. I would actually need to take this and multiply by 100. So if they're female relative to male, their predicted wage actually goes down by 0.25 times 100 would be 25%, right? That seems like a ridiculously large amount. It is what it is, right? I mentioned this is an older data set. There was likely a lot more discrimination going. I think this is even from like the 80s or something like that. But it's a pretty sizable effect, right? So that's still how we would kind of interpret these dummy variables, okay? And then kind of the dummy variable when we have that natural log as our dependent variable of y, okay? Holding everything else constant, right? So this is like really powerful. It's like it's saying take a male and a female, same years of experience. They're both either in the union or not. They have the same level of health, same race. They're in the same area of the country, either in a big city or not. Different. One of them is female. What's the impact on their predicted wage? That's a very powerful statement. Okay. So I just wanted to kind of mention that, thinking about, just trying to touch on things we've already talked about. So everything I was drawing up before, we were identifying the differences in the starting points. And I said the slope might be the same between your y variable and some other continuous variable. Well, it might always be I want to identify is one group being treated differently by a different group. Maybe I want to know, is the effect of a continuous variable, is that different across two groups? So here I have the same wage data, and I had this thought experiment of like, maybe females and males are being treated very differently in terms of how they look, right? I don't know how this data set was created. There was something about like the researchers had pictures of the individuals and they rated them from 1 to 5, which is entirely the most creepy thing I've ever heard. But that was a variable that existed in this data set, right? So we're going to use this variable and say, okay, maybe there, I don't think it's preposterous to believe that maybe firms treat people who are better looking differently than others. And you could argue economically, if I'm thinking about something like real estate, right, or something where I have to have a potentially there's a reason, they might do that for that person could generate more profits or something. There might be an argument for why that's not discriminatory, but it could also be discriminatory. So maybe my wages are higher or lower depending on what this beauty or looks rating was. Maybe my wages differ because I'm female or not, but maybe that effect of beauty on wages, maybe it varies for females compared to males, right? Maybe females' wages are treated differently depending on their looks, and maybe males aren't, right? So you could actually have an effect for one group of this looks beauty variable and not for the other. So we can include interactions not just between two dummy variables. I can include an interaction between a dummy variable and a continuous variable, right? So that's what I'm doing here, okay? So if we think about what these would represent, beta 2 is the difference in the starting point of wage, right? So I'll kind of write this out and give you a visual that goes along with this thought experiment. So I had in the slide, so I'm going to ignore the natural log for a second, and we're just going to think about wages to make it easier to talk about. So I had, let me make sure I'm lining this up with the slides. I think the first thing I had was, yeah, the beauty variable. I then had this dummy variable for whether or not they were female. And I then had the interaction between the two. Now, once again, if I'm doing this in Stata, to create this interaction term, it's simply taking that dummy variable, multiplying it by the continuous variable. Right? That's all we're doing there with the interaction. So if I think about, if I want to know what that relationship is between somebody's looks or this weird beauty measure we have and their wages, right? If someone has a 0 for that beauty ranking, what is their predicted wage if they're male? Well, if they're male, this would be a 0. This would be a 0, right? If we're looking at that beauty of 0, the predicted wage for a male starts out here. Now, by including that dummy variable, we've said what would the predicted kind of starting wage be for a female? I believe we find this is negative. So if I'm a female, right, if I'm looking at a beauty ranking of 0, what's the only thing that would get added in? Constant plus that coefficient on the female variable. So here, I think this is negative. So we're thinking about something like this. Okay? So that dummy variable still allows me for having a difference in the starting point between that 1 and 0 group for my dummy variable. But what it also does is say, okay, what is the effect of beauty? A 1 unit increase in that beauty variable for a male. Well, if beauty goes up by 1, wages go up by beta 1. If they're male, this interaction term would be equal to what? If they're male, this would be 0 times anything is 0. So here, this would be kind of like the effect of that beauty variable for who? The 0 group here, which was males. Now, if I think about the effect of this beauty variable for females, maybe it looks something like this. Why? If beta 3 is positive, what is the marginal effect of a 1 unit increase in X, or that beauty variable, for a female? Well, this is going up by 1 unit, so it would be beta 1. But if they're female, now when beauty goes up by 1 unit, it also gets multiplied by a 1, and we would also have added in that coefficient on the interaction term. So we now not only, sorry, I drew this at the same point. It should have started out down here, right? All right. So I not only can identify the difference in the starting point, I can identify differences in the slope across those two groups. Just to draw this out again, since I was not paying attention to what I was doing and talking too much. Right? So this is kind of like, here was our line of best fit for males. Here was our line of best fit for females. Right? So it's almost like if I had the data. So first, before I do this, because it'll get a little tricky, any questions on that idea? Okay with that? So really what we're doing when we have an interaction between a dummy and a continuous variable, it's almost like if we took two scatter plots. Right? Remember, these line of best fits, they're trying to give us an expected value of that error term, given the other values for X of what? Our expected value of the error term should always be kind of 0, right? That was the idea of our line of best fit. It's kind of like hitting that scatter plot of data like right in the middle. So it's almost like when I include the interaction term, I'm only looking at the observations for females and estimating that relationship between beauty and wages. At the same time, I'm only taking the observations for males and I'm estimating a different line of best fit for them. So I don't just have to have one linear effect that averages it out across two groups. It's almost like I took the data set, I created two scatter plots, and now I've got two lines of best fit, one for each group. And that ensures that now, because I'm controlling for these groups and allowing the marginal effect to vary, the errors for each group are now going to be 0, or the expected errors, I should say, right? It's, every observation has errors. We're trying to get this expected value of the error to be 0. If I didn't do that, and I tried to estimate this all at one time, maybe my line of best fit looks something like this. And it's going to be way off for females here and way off for males over here. Right? So essentially, when we include these interaction terms between a dummy and a continuous variable, kind of summarize it, we're essentially estimating two lines of best fit. One for the 0 group, one for the 1 group, or one for males, one for females in this example. Questions on this idea before we keep? Okay. So let's take a look at some regression results and kind of think about what we have here. So I kind of cut these off. There's a bunch of other controls. But if I'm looking here and I don't include the interaction term, so this is that beauty variable is called looks in the data set. It looks like the average effect of being female is pretty significantly negative. And the average effect of being one more unit ranked higher in terms of this looks variable was having a positive effect and very highly statistically significant. But this is where I'm like, okay, maybe that looks variable is being understated for one group and overstated for another. So let's include the interaction. Now, once again, you can use kind of that double hashtag without creating the variable. This is telling you that interaction term. You could create it yourself as well. So here, what would be the effects on wages of 1 unit higher looks rating or 1 higher beauty rating for male? Well, if they're male, this is equal to 0. So if looks goes up by 1 unit, the predicted wage of a male goes up by 0.039, and just barely not statistically. Actually, at the 90% level, what would I say the effect of looks is on males' wages? At the 90% level, do I reject or fail to reject the null? So I actually can't say that there's any effect. Now for females, right, is there a difference in that effect? Well, here, if looks goes up by 1, is there a difference in that effect for females? Well, the total effect of this looks going up by 1 would be 0.039 plus 0.049. So it looks like that it would be awarded kind of, or wages will go up by a slightly higher amount. But now our interaction term, if it's a continuous and a dummy variable, this is telling me the additional effect of this looks variable for the 1 group or for females here. Can I say that this looks variable has a different effect on wages for females? Not even, I mean, I shouldn't say not even close, right? We're pretty far away from our conventional levels. So this is good news, right? Males and females' wages weren't being treated differently depending on their looks. We don't find a difference in that marginal effect. Okay. But if we did, right, if this p-value is 0.05, well, then I would have evidence that the looks variable is actually having a positive, an even larger effect on females compared to the effect it's having on male wages. And here's where we have to start thinking a little bit harder about what is the total marginal effect of this looks variable for females. The total marginal effect, well, if looks goes up by 1 for female, it would be the looks coefficient plus the interaction terms coefficient. So the marginal effect is now going to differ for males versus females. What's one way to kind of think about why? So we've got to use a little bit of math here. So if I have that same regression here, I'll call it the way that our results had. So I had looks, I had female, and I had the interaction between the two. What is the marginal effect of that looks variable? Well, it's actually going to be different for both groups, but we can kind of see why. So if I don't worry about the groups yet, what is the marginal effect? It's essentially the change in wages, or my y variable, divided by a change in the x variable I'm looking at, or it's a derivative. If I take a derivative of this equation in respect to looks, I get what? Our estimate on beta 1. But when I take a derivative here, I would get our estimate for beta 3 times female. So now, if I'm thinking about what is the marginal effect of looks for a male, well, this would be equal to 0. The marginal effect is simply beta 1, right? That coefficient on that x variable I was looking at. But for females, or the 1 group, what is the marginal effect for them? Well, now this variable would be equal to a 1. The marginal effect for females would be beta 1 plus beta 2. So what is the difference in the marginal effect between the two groups? Beta 3. The difference between these two marginal effects is simply that interaction term coefficient. But this would be the total marginal effect for both groups. Any questions on this idea before we keep moving? Where are we at in time? I think I'm probably long-winded here. Say, okay. Any other questions? I want to make sure we get a good setup because we won't get there today, but you can maybe already imagine what's the next type of interaction I could probably do. If I had a dummy and a dummy, I had a dummy and a continuous variable. The next thing I could do is a continuous and a continuous variable. It's going to be a little bit more complicated. Okay. But at this point, I'll look at one more example and stay to here today. But I just want to kind of throw this in there just for like always trying to give you kind of maybe we keep it a little more basic in this class, but like the next level. So if I can identify differences between two groups, what if I had dummy variables for every single race? And I want to know maybe how does, I don't know, the SAT score impact a Y variable, which is a 1 if they're admitted to a university or 0 if not. All right. So the thought experiment here, try to come up with these off the top of my head sometimes. We'll see if this is a good one, right? Or we could call this, was I admitted to the university or not? So it's just a dummy variable as my Y variable. We can do it with continuous variable as well. Here's just a different example. So let's say I wanted to know, okay, what's the impact of someone's SAT score? All right. So I think if your SAT score goes up, it's likely that you're more likely to be admitted. All right. It's likely going to be positive. But maybe I think that when universities look at people of different races, maybe they're treating them differently. The same SAT score could be treated differently if I'm white, Hispanic, etc. I don't just have to create a dummy variable, 1, 0. What could I do? I could actually do a control for like every single possible race. And then I could also include, I don't know, maybe we'll look at beta 7 here, an interaction between every categorical, right? Every one of these different races and the SAT score, right? So what is that going to allow me to do? So I don't know, maybe here we got, we can do a bunch of different, however we identify race, right? I understand race is a much more complicated issue than simply creating these dummy variables, but if we look at data sets, that's often how it comes out, right? That ticket stop data, they had one for every, different category. Well, now we can pick up, here's the effect of the SAT score on whether or not I'm admitted or the change in the probability that I'm admitted to that university. But we're now allowing for the effect of that SAT score to vary across every single racial group. So what can we now identify? Is the university treating the same SAT scores differently across different races? This is very useful, right? So this is like another thought experiment kind of example. We don't just have to have an interaction term between this continuous variable and one dummy variable. We could technically, if we have several groups, like a categorical variable, we could create an interaction between that continuous variable and every single dummy variable, right, that would exist for that categorical variable. In this case, I chose race. Okay. Hopefully these are all statistically insignificant and there's no difference in that marginal effect. I don't have a fun data set that looks like this at college admissions, but this would be something, probably find it out there. Ask ChatGPT if one exists, and there probably is, right? But I don't know where it exists. So does this make any sense? Any questions on this idea? I won't push you guys this far. I'll kind of keep it an interaction just between one dummy variable and a continuous variable, but you could start to do something like this. All right. So I have maybe let's see, a March Madness example here for today. So we'll come down here. I've got this NBA shots data. Hopefully I have it correctly on my OneDrive. Yeah. So here I'm going to create, I could do this two different ways. I think here I'm just going to do, let's just do the tall one, just for the sake of time. So I'm going to create this indicator for whether or not an NBA player was tall. So this is what? 5 feet is 60 inches. No, sorry. Yeah. So this is going to be what? You're above 6'8", right? This is a tall person, right? Above 6'8". I could change this if I wanted to. So this is just a dummy variable. It's a 1 if the person was over 6'8", 0 if not. I could run this regression and it looks like, oops, I hit the wrong button. So now it's going to get mad at me. Oh, I already defined it because I'm clicking too fast. Looks like tall players actually shoot a little bit better. Well, why? If I'm a tall player in basketball, you might not have the knowledge about the sport, but where are most of my shots being taken from? Really close to the rim, right? What becomes harder? Where do you see the percentage of the shot being made go down? Further from the basket. I haven't controlled for any of that. So I'm going to go back in and I'm going to include some of my controls for it. Well, where was the shot taken from? Shot distance. Now, I'm also going to think about, okay, well, maybe a player who's the kid from Florida is like 7'9". I think he's on the bench, but he's just crazy tall, right? If he's at a foot away from the rim, he's going to be making it way easier with people defending him than if someone's 5'2", right? And so maybe there's this interaction. The effect of how far away I am from the basket varies with the player's height. So I've included an interaction term between whether they were identified as being tall and how far away they were from the rim or shot distance. So I have a dummy continuous variable interaction term. I then included a bunch of additional controls. So I have this data set. I've used it for some papers and played around with it. You've got the attendance of the game, what the player's average field goal percentage is outside of this game, the point gap, how close the game is, what the closest defender is, the angle the shot was taken, all these different controls. This should kind of help us kind of get at this. So let's say I run this regression with all these additional, what did I do? We weren't looking at centers here. What variable was I looking at? It was this one up here, right? Whether or not they were identified as tall. So if I run this regression, we can now think about what is the impact or what is the marginal effect of being further away from the basket. And here, if the y variable is just whether or not I made it, it's going to be changed in the probability of whether or not I made the shot. So if I believe shot distance was like 1 foot further away from the basket. If I'm 1 foot further away from the basket, the probability I make the shot goes down by 0.003. Okay, so pretty small effect, but it's highly statistically significant. Not breaking news here. Further that the player is from the basket, usually their free throw or field goal percentage goes down. However, if we think about what is that effect on someone who is very tall? On that, stereotypically in basketball, we think of taller players usually aren't as good as shooters, right? So the marginal effect of being 1 more foot away from the basket, if I'm identified as tall, you would think maybe it's negative, right? Here, it's still positive, right? Or sorry, you would think it would be an even larger negative value. Here, that interaction term has a positive coefficient, which actually means as they move further from the basket, they're actually a little bit more likely to make it than someone who's not tall. Now, maybe there's omitted variable bias, right? So these interaction terms can still fall victim to omitted variable bias. So maybe I don't have the right controls. But this is what the data is telling us, right? That marginal effect is varying due to someone who's tall and not tall.
That could be because a lot of the guys that are taller are really taking
as many shots.
Yeah, so maybe what's one omitted variable I didn't include here? How many shots are taken at various points, at various distances away from, right? So there's issues we haven't talked about in this course that are probably driving this result to be counterintuitive. But it just means that we need to learn more. We need to kind of continue on with regression analysis to figure out why this might not be what line up with what we're thinking about. But based off what we talked about to this point, this is how we'd approach it. But once again, we likely have some omitted variable here. The number of attempts taken at different distances would probably be an additional good control that we don't have in here. Yep. So like field goal attempts might be even if I control for that might be.
Like also like the guys don't shoot and also I feel like they take more
Yeah.
control.
So let's think about this. What are you saying? You were saying they're taking more shots when the defender is. So what might I want to include? An interaction term between shot distance and defender distance. We haven't gotten continuous interactions yet, but it's the same thing. If I don't include an interaction term that should be in there, what have I created? Well, I don't have an important variable in my regression. I've created omitted variable bias. So maybe that's an additional interaction term I want to include. You don't just have to have one interaction term. You can include several, right? Maybe be across multiple variables here.
So you can like field goals, for example, the same trivial sample size, because I see LT and stuff like greater than more than 30 shots. That's something you could. Like what would if you
I mean, you can create, right? Like if I haven't, I could control for the number of free throw attempts. I could control for the number of free throw attempts within 5 feet, as well as the number within 5 to 10 feet as well. I can create all kinds of dummy variables based off of continuous variable, right? We won't dive into some of the issues that could exist with that. You have to think a little bit harder about what you're doing. But yeah, you could start to create additional variables from your data set, to create additional dummy variables that would be additional controls. Any other questions on this idea? Okay. I think maybe to end here, I'm going to do this real quick. So I'm going to create this variable for whether or not they were centered. So instead of just using their height, so I've got my Purdue shirt on today. So like Robbie Hummel was over 6'8", and like he was a great shooter, right? So maybe height isn't like the perfect measure. Maybe I want to look at the position, right? I'm really making sure I'm just looking at these centers who typically aren't as good as shooters. So if I do the same thing, but I include interaction term there, now if I look at my results, okay, this still goes against what I would think, right? So whether or not I use their height or their position, the impact of being 1 foot further away from the rim, if I'm not a center, right? I'm not one of these, and that's not my listed position. That probability I make the shot goes down by 0.003. So probability, so I can think about this like 0.3%. But if I'm a center and I move 1 foot further from the rim, the total marginal effect would be what? Negative 0.003 plus 0.002. I'm still not as likely to make the shot, but that decrease in the probability is not quite as large magnitude, right? And it's all highly statistically significant. So these are interesting results, right? Maybe I just need to do some further exploration as what we've kind of talked about. Like maybe there's some things I'm not controlling for that I want to make sure I am. Now, why are these all highly statistically significant? Just going to hit on some concepts we talked about before. What helps me find statistical significance? How many observations do I have here? 35,000, right? So very large data sets, it's going to be a lot easier to find statistically significant results. I don't know, maybe one that's kind of interesting to me was that even if the game is close or not close, doesn't seem to impact. So these players aren't really impacted as much by, I think maybe it's, maybe they're just driven by wanting to perform better. They don't care if it's going to help them win the game or not. But, these are, you could use any data set you're interested in. You could start to include these interaction terms to pick up, is there a difference in the marginal effect of a continuous variable across different groups? So this is kind of where we're leaving off. We're looking at differences in slopes. I think I had some of the looks stuff here. This was a paper that actually used that. So they found this kind of difference. This was a different data set than what we looked at. So it wasn't this beauty one, but they actually had data. This is like a field experiment on the number of, so weird. So what they did was they used PhD students and they went to their like LinkedIn profile, pulled the picture, looked at their application, saw the number of interview requests they got, and then did a similar thing where they had a group of other like 100 individuals rate these people on like a looks rating of 1 to 10. Right. So it wasn't just like one person, right? It was across, like they were having these kind of experimental groups. And then they're doing the same thing. They interacted with female with beauty and said, did they get a higher number of interview requests if their LinkedIn profile page was rated higher? This was kind of what they looked. These are the 2 lines of best fit they found, right? This is discouraging, right, for our society, right? There was almost no impact on males, slight positive effect. So this was, they got put in certain percentiles of attractiveness. For females, I mean, this is a pretty sharp, right, kind of increase, right? So, I mean, this is, this is the power of kind of what we can do. And we were looking at it with a much simpler data set. We know allows us to identify some real issues that might exist in society. And you can imagine why like firms might want to kind of be looking at this. So we will kind of leave off there. We will start next week. We'll do more interaction terms with continuous variables. Things are